So, welcome to this lecture on Static Semi 106. And in today's lecture, we will going to discuss about the method of virtual work. Uh, Now, as the name suggests, that this method is basically it uses the concept of energy because work is actually a form of energy, and these energy methods are uh, useful concepts in mechanics. Uh, so you all know that when the bodies are in equilibrium, rigid bodies are in equilibrium, they generally remains at static position, rest position. So the work done in this method actually remains hypothetical. uh, that is the word, that is the meaning of the word virtual here. The work done remains hypothetical, or you can say that it does not really exist. We just anticipate it, we just assume it. But the quantities that you will going to calculate, like forces, angles, moments, they will be realistic. So you can apply this concept of virtual work to rigid bodies and particles both. But as a matter of fact, this method is best applicable to system of connected rigid bodies like frames and machines. It will be most helpful when you are dealing with frames and machines. So why we are basically studying this method of virtual work? Because it can be considered as an alternative method of analyzing the bodies in equilibrium. Now in chapter number 5 you have already studied how to analyze the equilibrium of rigid bodies by using equations of equilibrium. Submission of forces must be zero, submission of moments must be zero, and you have a lot of equations, and you can solve them simultaneously to get the desired quantities. So you have learned this technique of analyzing equilibrium of rigid bodies. Now, this method of virtual work is basically an alternate method. So without actually going into rigorous derivations, we would like to focus on the fact that virtual work of a force is basically defined as the product of force. Okay, the product of force times the virtual displacement, and this virtual displacement is a very tiny small quantity, differential quantity. So as you know that work is basically a scalar quantity, so when the direction of this force and this virtual displacement delta r is same, then the work will be positive, otherwise it will be a negative work. And as force can perform work on the body, a moment can also perform work. So the virtual work done by a couple moment acting on a rigid body is the product of the value of moment and the uh, infinitesimally small rotational displacement delta theta. Now please remember that delta theta and delta r are very small quantities. Okay, so please note that delta r and delta theta are very small quantities, and therefore they are first order differential quantities. That is, you have to remember the point that delta r and delta thetas, they can be calculated by differentiating certain expressions. Okay, so what are those expressions? We will going to uh, tell you in a while. But before we proceed, you first have to again look at these expressions, and these are the expressions for virtual work of a force and virtual work for a couple moment. So virtual work of a force is basically the force times infinitesimally small displacement delta r or virtual displacement delta r, which actually does not exist, but we just assume it to exist. And similarly, the virtual work of a couple is the value of the moment, couple moment multiplied by a very small tiny quantity delta theta, or differentially small rotational displacement delta theta. And this work, the work of couple moment, can be positive if the sense of the applied moment and the sense of the rotational sense of the applied moment and the rotational sense of the theta is same. Otherwise, it will be negative. And here, as I have already told you, that F and delta R, if they are in the same direction, the work will be positive, otherwise negative. Now, these are the formulations that you have to remember. These are the formulas, how you calculate the virtual work of a force and virtual work of a couple moment. So we now know that these delta r and delta theta are basically very small, infinitesimally small differential quantities, and they are basically the first order derivatives. Uh, and how these derivatives will be established in our problem, we actually have to consider the geometry of our problem and the space variables. And what are the space variables? The x y variables of our space, if we are dealing with two-dimensional problems. So we will going to have some expressions that will relate the space variables with the geometry of our problem, and from these expressions we will be able to generate the virtual displacements delta r and delta theta by differentiating them, by taking the first order derivatives. Then what is the principle of virtual work? So if a rigid body is in equilibrium, then the algebraic sum of virtual work of all the active forces and couple moments acting on the body is zero. So this expression is giving you the one and only expression of principle of virtual work that we have to use in all the problems related to this method. You have to algebraically add all the work done by the active forces and couple moments acting on the body and equate them to zero, because originally our rigid body is in equilibrium, and so it will not going to displace, or any part of the body will not going to displace. These displacements are just virtual, they are hypothetical, assumed. They do not exist in reality. That is why it is known as the method of virtual work. Another point that you have to remember for the time being is that only active forces will be able to do work, or active moments will be able to do work. Okay. So active loads, that is active forces and active moments, are those forces and moments uh, which will going to act at locations on the rigid body that will be displaced by some amount, and locations and positions on the rigid body that are not allowed to displace any kind of force or moment acting on those locations will be considered as non-active force, and it will not going to participate in the principle of virtual work. So keeping these points in our mind, we will demonstrate the procedure of using the method of virtual work to problems. And as I told you, that these this method is best applicable to the situation where the rigid bodies have interconnected multiple members like frames and machines. So our problem will be related to these structures like frames and machines. It does not mean that you cannot apply the method of virtual work to equilibrium of particles or equilibrium of single rigid body. You can apply, but it will not be very useful in those cases. Okay, the maximum benefit of this method will be extracted when you are applying this method on analyzing frames and machines. So let us look at this problem 11-5. It says that determine the force developed in the spring required to keep the 10-pound uniform rod AB in equilibrium when theta is 35 degree. So at the equilibrium position, this theta is 35, and we need to find the value of the force in this spring. So this spring must be taken as active force. Okay, we cannot avoid this force because we need to find the value of this force. And you can also see that this force, this spring, is connected with point B, which will be allowed to displace. So when you will apply this moment of 10 pound fit per 10 pound fit on this rod AB, this point B will going to displace. Okay, just hypothetically, it will going to displace. So that is why the force associated with this point, that is the spring force, will be an active force. Similarly, when this moment will going to act, it will going to rotate this rod AB about point A in the clockwise direction, and that will going to bring its center of gravity downward. So the center of gravity is also one point on this in this figure, in this structure, that is going to be displaced, and the force associated with this point is the weight of the rod AB, that is 10 pound. Okay. And similarly, this couple moment of 10 pound fit which is acting on the rod will going to alter the value of this theta by a very small tiny amount, that is delta theta. Okay, so this is also an active force. But if you look at the support reaction of the pin at point A, you will observe that point A is basically not moving at all. It is fixed. So any kind of force acting on this point, whether externally applied force or support reaction of this pin, okay, they will be considered as non-active forces and will eventually not going to take part in the calculation of work. So you have to look at this problem carefully, and you have to anticipate, you have to assume in your mind, realize in your mind that when this couple moment of 10 pound per foot is applied in a clockwise direction on this rod, then how this rod will going to be displaced, only hypothetically. Okay, so you can realize the fact that it will going to be displaced something like this, whereas this point B will going to travel on a arc, circular arc, and this point B will going to then come here at this point. Okay. So from this point it will going to come at this point, and the center of gravity will going to be displaced in the downward direction and will appear here, and this rod has been displaced by an infinitesimally small rotation delta theta. Okay, so this is an active force W that is acting at the center of gravity. This is an active a load moment, and this spring force will be stretched because you can see that this point B has actually moved in the forward direction while it is traversing this circular arc. So this force, this spring force, will be an active force and it will be tensile in nature. So tensile forces always acts away from the point of contact. So this is a picture that you should have in your mind before starting this problem. You have to look very carefully that which points will going to be displaced and in what manner before sketching its free body diagram. So here I have shown its free body diagram in a more elaborative manner. So at first I have identified that this point A is not moving at all. So let us take this point A as my reference point, and then I know that point G, which is the center of gravity of this rod, will be displaced, and this point B will going to be displaced. So let us locate these points, the position of these points, the initial position of these points by defining the space variables. So I have defined a space variable yg that is locating the initial position of the center of gravity G, and I have used a space variable xb that is locating the initial position of point B. This is the first thing that you have to do. You have to select a point that is fixed, take it as reference, and then from this reference point you locate the positions of all the points on your free body diagram on your rigid body that are likely to be displaced under the action of the given load. And you have shown here the reaction of the pin AX and AY, but we know that these reactions are uh, mm, non-active forces. Okay, so they will not going to participate because this point A is not moving, it is fixed. So the amount, a very small amount that this point B is displaced, okay, is basically the virtual displacement of point B, uh, considered as delta S xb, and a very small amount, this center of gravity has been displaced, okay, from its initial position is considered to be the virtual displacement of the center of gravity delta yg. So this is y because this is delta yg because it is displaced vertically. This is delta xb because it is displaced horizontally. And when this point B will be stretched by an amount delta xb, this spring will going to be stretched, and so the force in this spring will be tensile. So therefore I have shown a tensile force that is acting away from point B, and this weight of 10 pound is acting at center of gravity in the vertical direction. This is the applied moment that is acting on the body, and this is the amount of very small rotational displacement delta theta. Now the first thing is, I have to establish the equations that are going to relate these space variables with the geometry. So you can see that this xb can be related with this theta through the geometry of this figure, this right angle triangle. If you consider this right angle triangle, you will see that xb is nothing but 6 cos of theta, because 6 is the length of this rod AB. And similarly from this small triangle, you can relate this yg with this theta, and this yg will be equal to 3 sine of theta because the center of gravity is located at 3 foot because the total length is 6 foot. So by using the geometry and this angle, this common rotational displacement theta, I have related xb and yg. Okay. Now in order to obtain delta xb and delta yg, I have to differentiate these expressions. And remember, I told you that the virtual displacements delta xb and delta yg are first order derivatives. So we have to take the first order derivative of these equations to find out the values of delta yg and delta xb. So by differentiating with respect to theta both the sides of equation 1, we will get delta xb is equal to negative 6 sine theta delta theta. So the derivative of cos theta is negative sine theta, and delta theta will going to appear from here. This delta theta is originally here because we are differentiating with respect to theta both the sides. So the result will be minus 6 sine theta, and then in the end, to find the value of delta xb, you can bring this delta theta here. So please note that delta xb has been written in terms of delta theta. Similarly, when you will differentiate this expression of yg with respect to theta both the sides, you will end up writing delta yg equals to 3 cos theta delta theta. The derivative of sine theta is cos of theta delta theta. Okay. So we have obtained the values of virtual displacements that are nothing but the first order derivatives of these equations that we have developed by considering the space variables and the geometry. These are the first two steps, sorry, the first three steps. The first one is uh, the you draw the complete free body diagram. So you show all the known and unknown forces on this diagram, and you show all the appropriate displacements. Okay. The second step is to use the geometry and space variables to relate them. Okay. The third step is to calculate the virtual displacements by just differentiating these expressions. And the fourth step will be to uh, write down the expression for virtual works. So work done by the active loads. AX and AY will not going to produce any work because they are acting at a point which is not moving at all. So these goes out of the consideration. This moment is trying to rotate this rod AB in the clockwise manner. Okay, and because of this, this theta changes by a very small amount, delta theta, which is also in the same direction, rotational sense, as this moment is. So therefore, the moment, the work done, the virtual work done by the moment will be positive. M delta theta will be the work done by the moment, as I showed you on the first slide of this lecture. The work done by the moment is the product of value of moment times the infinitesimally small rotational displacement delta theta. Work done by the weight of the rod will also be a positive quantity because the direction of this force, this weight W, and the direction of this displacement of point G, delta YG, is basically same. So it is a positive quantity, W times delta YG. So it is in the same direction of the force. Okay, so you can imagine that in general, the work done by a force, uh, okay, let's say if this is theta, and this force F tries to move a body, displaces a body in this direction, which is equal to dr, then the component of dr in the direction of F will be dr cos of theta. Okay, so the work done by the force in general can be written as F cos theta dr. as as I showed you on the previous slide. So this dr can be written as uh, delta r if you consider it to be a virtual work. Okay. But here you see that there is no need of cos theta term, because this deflection delta yg is exactly uh, in the same direction. It is not making any angle. So it is W times delta yg. And you see that the work done by the spring force will be negative, because the direction of Fs is completely reverse of the direction delta xb. So they are in the opposite direction. So that is why this work done will be a negative number, delta Fs delta xb. The next step is to use the principle of virtual work. So we use the principle of virtual work, which states that uh, sum of all the work done by the active forces and moments will be zero. So we just add these works that we have calculated with respect to their signs and equate them equal to zero according to the principle of virtual work. And we have to find the value of Fs. Okay, we know the value of M, we know the value of delta yg and W, we know the value of delta xb, and these delta yg and delta xb are also in terms of delta theta here. So we just substitute those results here, and we realize that this delta xb is actually negative. So we have to use this negative sign here with delta xb as well, and this negative is because of the negative work of this spring force, because we assumed it to be in the negative x direction, and we assumed this deflection to be in the positive x direction. So therefore they are both opposite to each other, and therefore their work was negative. And this delta xb also comes out to be negative. So this minus and minus will make it plus. And one more thing you should note here, that all these virtual displacements delta yg and delta xb that we have calculated here, they are basically expressed in terms of delta theta, and so delta theta here will going to cancel out. So delta theta will going to vanish from the equation, and this is a very important point to note, because if you have done some mistake, okay, you will not be able to remove this uh, common rotational displacement delta theta. And I'm saying I'm calling it common because you see that uh, these space variables, both of them can be related to this common angle theta by using the geometry, the right angle triangles. So that is why I'm calling it delta theta. I'm calling this delta theta as common. So this common rotational displacement should cancel out from the equation. Okay, this is an indication of that you are doing the right thing. Now theta is already known to me, which is 35. M is known to me, it is 10 pound fit. W is known to me, it is 10 pound. So I can easily calculate the spring force from this equation by just substituting the values. So first I make this Fs my subject, and then substitute the values of moment, that was 10 pound fit, W that was 10, theta that was given to be 35 degree, and I directly calculated the value of spring force, which is minus 10.046. So this minus actually has no significance here. It is just telling us that this direction of Fs could be towards point B. Okay, since these are not equations of equilibrium, so we should not bother about the minus sign. It is just telling us that this entire deflection can be the other way around. So you have realized that we didn't actually utilize the values of these support reactions AX and AY. Okay, and we have calculated the value of spring force. So we cannot take this Fs as non-active force because it is to be required. We want this value Fs. So please remember that all kind of forces or moments that you are required to find out, you cannot consider them as non-active forces or loads. So we move on to the next problem, 11-9, and it says that if a force of 100 Newton is applied to the lever arm of the toggle press, and determine the clamping force developed in the block when theta equals to 45. So this when this theta becomes 45, we have to calculate the uh, force that is being applied by this block to this workpiece E. Okay, so you again have to look at this figure carefully, and you have to imagine in your mind that when this vertical force P is being applied at point A in the downward direction, then how this mechanism will going to uh, be deflected, how this mechanism or these links will going to deflect, because eventually you know that this is basically a machine. It's basically a machine which has interconnected members, and it is utilized in compressing this workpiece. So this arm DC, this member DC is basically applying a compressive load on this workpiece E. So that compressive load could be the load in the vertical direction. Okay, and this point A would move in the downward direction. Okay, rotating this arm AB by some very small, infinitesimally small rotational displacement delta theta, and this will going to cause this part BC to rotate, and similarly it will going to cause this member DC to straighten up. And when this member DC will going to straighten up because of this infinitesimally small rotational deflection delta theta, this will going to apply a compressive force on the workpiece. So we have to find out this compressive force. Okay, and this should be a tentative uh, deflection curve of this machine. Please note that this point B is again a pin joint, and this is inactive because this point B is not at all moving. Right, this point C is moving, but we can say we can clearly see that this member DC is a two force member. Okay, so whatever forces are acting at this location C, they are equal and opposite at this location D. So if you consider two reactions of the pin at point C, Cx and Cy, then the reactions at point D or at pin D will be dx and dy. But these two reactions dx and dy will going to form a resultant force acting at D, and these reactions Cx and Cy will going to form a resultant force acting at point C, and these two resultant forces will be equal and opposite and will be collinear because this is a two force member, and we have studied uh, about two force member in chapter number 6. So it does not matter whether you use forces at this point or you use forces at this point D. Please remember that only the vertical component is important for us, because it is only the vertical component of this two force member DC that is basically applying compressive load on this workpiece. So let us redraw these images that we have generated in our mind so far in a on a clearer picture. So you can see here that when this force P will be applied at point A, it will displace point A in the downward direction by an amount delta YA, which is the virtual displacement of point A, an infinitesimally small displacement, and this lever AB will be deflected or rotated by an amount delta theta, and similarly this lever BC will be rotated by an amount delta theta, which will cause this member DC to rotate and apply a force in the vertical direction to this workpiece E, which is the compressive force that we want to calculate. So this point D will going to move in the upward direction as this two force member DC will try to straighten up because of this rotation, delta theta or delta YA movement in the downward direction. And you can see that this point B is basically not moving at all. So the loads acting at this point, that are the pin reactions Bx and By, they will be non-active forces. So the active force, one of the active force is this one, applied force P. The other active force will be Fd. We have to calculate Fd. So before we proceed, we have to actually mention the space variable. Okay, so I know that this point D will going to move in the upward direction in order to apply this compressive force on this workpiece E. So I have to locate the position of this point D using a space variable with respect to the reference point B, which is not moving. And this space variable, we say that it is YD. Okay, so from this point which is not moving, we can consider this point as our reference point, and we locate the initial position of point D. On our diagram, this is the space variable YD. Then the amount that this point D moves in the upward direction is the virtual displacement of point D, that is delta YD. The amount this point A moves in the downward direction is the virtual displacement of point A, that is delta YA. And these are virtual displacement in rotational formats, delta theta. So again, the first thing is to consider the geometry and try to relate this space variable YD by using the geometry of this deflection diagram or this entire free body diagram. So if I drop a perpendicular from point C, I can end up in making two right angle triangles. Okay, so this height is nothing but 0.2 cos of theta, and this height is nothing but 0.2 cos of theta, because this is 0.2 meters and this is angle theta. So this is 0.2 cos of theta. Therefore, this YD is actually equal to twice of 0.2 cos of theta. And this delta YA can be written as 0.5 times of delta theta, because this is a very small amount of rotational displacement given, and we can actually relate this very small amount of displacement by using the equation S equals to R theta. So similarly, this delta YA can be related to the radius, that is 0.5 meters, and this angle delta theta. So this will become delta YA equals to 0.5 delta theta. And again, you see that I have represented the virtual displacement delta YA in terms of the common rotational displacement delta theta. Similarly, YD has been related to theta. Now the second part is to calculate, the third part is to calculate the virtual displacements. So delta YA has already been written in terms of delta theta. This YD is 2 times zero point 0.2 cos theta. So by differentiating the expression of YD with respect to theta, I can write down the expression for delta YD, which is minus zero point 0.4 sine theta delta theta. Now, once you have written this expression, you again note that this virtual displacement delta YD has been represented in terms of delta theta. As I mentioned that in this problem, we have only two active forces, this applied force P and this compressive force Fd that we want to calculate. So there will be two works only. This Bx and By is basically a non-active force because it is this point B is not moving at all, and CD is a two force member. So only the vertical component of this two force member uh, is required, which will going to compress this workpiece. So that we have considered as FD. So the work done by the force P will be positive because the direction of P and delta YA are both in the same sense. So this work is positive. The direction of FD and the virtual displacement of point D, that is delta YD, are both in the same direction. So this work will also be positive. Therefore, applying the principle of virtual work, uh, we will have this equation P delta YA plus FD delta YD equals to 0. And now we substitute the values of delta YA, which is zero point 0.5 delta theta, and delta YD, which is equal to minus zero point 0.4 sine theta delta theta here in this equation. And so we again see that this common deflection delta theta cancels out from our expression, and we are left with only these quantities which are known to us. P is given to be 100 Newton, okay, and theta is given to be 45 degrees. So we can easily find the value of FD from this expression. Just by putting the values, we are able to find the value of FD, which is 176.77, which is equal to 177 Newton. So after solving this problem, you might have realized that we did solve some problems on machines in chapter number 6, and there we see that if we are to use the equations of equilibrium in analyzing machines, then we have to really dismantle different parts of that machine and analyze the equilibrium of each and every part separately, thereby making a lot of equations and then solving them simultaneously to find out the required quantities. So that method was actually lengthy. On the other hand, the concept of virtual work has actually reduced our effort. Okay, in this we do not have to dismantle each and every member and analyze it separately. We just have to come up with a vision of how this entire mechanism will be deflected under the action of the active forces. Okay, and by using the concept of virtual work, we can really find the desired quantities, so thereby reducing the uh, solution time and effort. This is the advantage of using a method of virtual work. So it is an alternative method of analyzing equilibrium of rigid bodies, and this actually brings us to the end of the course Static Semi 106 in this semester. I hope you might have learned a lot of new concepts which will definitely be helpful for you in future courses to come. And I would again request you all to go through these video lectures again and again uh, carefully, prepare your notes, and get yourself ready. Thank you.